Okay, let's dive right into this. Today, we're deconstructing something you literally walk over every single day, the ground beneath your feet. We're going to translate the dense academic geology of soil genesis entirely from our source material into a highly structured mathematical journey. We've got 6 logical stages to unpack today. We'll start with the parent foundation and the genesis equations, then break out the active and passive factors, and finally, we'll wrap up with the stages of weathering and the soil catena. Let's get to it. First up, Section 1, the parent foundation, or, as pedologists call it when looking deep into a trench, the sea horizon. So, what's really interesting about this slide is how the method of transportation drastically alters the soil's final potential. The source material defines this parent material as the unconsolidated, chemically weathered mineral or organic matter that soil develops from. Basically, it's the raw material. Now, check out the top row. When water acts as the transportation agent, specifically rivers, it deposits sediments called alluvium. When these form alluvial fans where streams leave narrow valleys, the resulting material is usually super agriculturally productive. Contrast that with gravity on the 4th row down. Gravity creates colluvial debris by dragging detached rock fragments down slopes. Because this is driven by physical weathering and frost action, these colluvial deposits are coarse, stony, mostly inaccessible, and just have terrible characteristics for agriculture. So the transporting agent absolutely dictates the baseline potential of the ground. Moving into Section 2. The genesis equations. How does mathematical soil actually form from those raw deposits? Well, it isn't random. It's a calculated interplay of forces. This concept was first put forward mathematically by Dokuchaev in 1889, and Hans Jenny perfectly captured it in his 1941 work. He stated, "Soil is a dynamic natural body having properties derived from the combined effect of climate and biotic activities acting on parent materials over a period of time." This is absolutely critical to remember. Soil isn't just dirt, it's a dynamic mathematical product. And here is that exact concept translated into Jenny's famous equation. S, or any given soil property, is a function of 5 distinct variables. Cl is climate, B is the biosphere, or organisms, R is relief, meaning the topography, P is that parent material we just talked about, and T is time. Every single handful of soil on Earth is the solved product of this exact mathematical function. To really make sense of this equation, a researcher named Joff brilliantly grouped these 5 variables into 2 distinct camps: active factors and passive factors. The active factors, climate and organisms, are the heavy lifters. They supply the actual energy, the heat, the water, and organic acids, to drive soil formation. The passive factors, parent material, relief, and time, don't supply energy. Instead, they act as the raw mass, or the canvas, that the active factors are continuously working upon. Which brings us to Section 3, active soil-forming factors, the energy suppliers. So the crucial point here is that among all the variables in our equation, the source material explicitly calls out climate as arguably our most influential factor. It acts directly by supplying water and heat, and indirectly by dictating the local flora and fauna. Because of this, there's a constant, invisible tug-of-war happening in the ground. When climate is so dominant that it completely obliterates the original effects of the parent material, pedologists classify the resulting soil as ectodynamorphic. But when the climate is weaker and the parent material still stubbornly holds supreme influence over the soil's characteristics, it's called endodynamorphic. It's a fascinating battle for supremacy right beneath the surface. We can clearly see this active power of climate when we contrast rainfall levels. In humid regions where rain actually exceeds potential evapotranspiration, water leaches basic elements straight out of the ground. That decreases the pH, making the soil acidic. But because vegetation absolutely thrives there, these soils boast high organic matter and clearly defined horizons. In stark contrast, arid and semi-arid regions just don't get enough rain to flush the system. Bases accumulate, the pH goes way up, and the soil struggles to develop any distinct horizontal layers. And then there's temperature. The number 10 you're looking at represents Van 't Hoff's law. According to the source, for every 10 degrees Celsius rise in temperature, chemical reactions in the soil increase by a factor of 2 or 3. No way, right? It literally means that as temperatures climb, biological activity and chemical decay skyrocket. This is exactly why weathering processes are vastly faster and more intense in tropical climates compared to temperate ones. The other active factor is the biosphere, or biota. The type of vegetation radically alters the ground. Grasslands, for example, create soils with exceptionally high organic matter in the subsurface and really strong structural stability. Coniferous trees, on the other hand, drop needles that are super low in basic cations like calcium and magnesium. This leads to rapid leaching and highly acidic soils. Meanwhile, deciduous trees, like oaks and maples, drop a continuous litter that actively cycles nutrients, creating base-rich soils. The plants aren't just passively sitting there, they are actively engineering the soil from the inside out. Let's transition to Section 4, Passive Soil Forming Factors. The physical constraints. And this brilliantly illustrates what we meant earlier. Passive factors might not supply the energy for the chemical reactions, but they profoundly dictate the ultimate destiny of the soil profile. Look at how the passive parent material exerts its influence element by element. As the rock decays, it releases specific elements that passively program the soil. Silicon and aluminum provide the rigid skeleton for secondary minerals. Iron and manganese dictate oxidation and literally paint the soil its characteristic red colors. Sodium and potassium act as dispersing agents, while calcium and magnesium have a flocculating effect, which basically means they clump particles together. That creates a highly stable structure that's ideal for plant growth. The next passive factor is relief, or topography. This can radically hasten or delay the work of those active climatic forces. On gentle, flat topography, soils tend to be thick, they retain a more humid internal climate, and they actually age faster because the materials stay put and weather in place. But on steep slopes, accelerated erosion strips the surface material away before it ever has time to mature. The result is that soils on steep inclines remain perpetually shallow, stony, and weakly developed. Which brings us to the final passive factor, time. Time is absolutely crucial for a soil to develop distinct genetic horizons. But here's the catch. Time works differently depending on where the soil is located. Generally speaking, soils age much faster on flat to gently sloping uplands. Conversely, soils sitting in river floodplains remain permanently stuck in a young state. Why? Because the periodic flooding constantly erodes the old material and piles on brand new sediment, continually resetting the geological clock. Section 5. The stages of weathering. Let's look at the chronological life cycle. Once these active and passive factors interact over time, a very specific life cycle emerges. It starts at the initial stage with completely raw, unweathered parent material. Then comes the juvenile stage, where weathering has started, but you can still clearly see the original rock. By the virile stage, all easily weathered minerals have been completely decomposed, but the senile stage is where it gets really fascinating. At this point, the soil has been weathered so extensively that only the absolute most resistant minerals, like quartz, manage to survive. Finally, it reaches the final stage, where soil development is considered totally complete under the prevailing environmental conditions. And our final section, Section 6, the soil Catena sequence. Let's move on and see how this all builds into the concept of the soil Catena, developed by Milne. A catena represents a regular, repeating sequence of soil properties found along a topographical slope. Even if the parent material is exactly the same, the sequence shows a highly predictable shift in drainage. At the upper slope, you find well-drained soils. But as you follow the topography down to the base of the slope, the drainage becomes impeded. This change in drainage naturally shifts the type of vegetation that can grow, which in turn feeds right back into our active soil-forming equations, creating distinctly different soils from top to bottom. It's like a giant interconnected puzzle. So, having decoded these strict equation-driven forces detailed in the source material, I want to leave you with this final thought. How does your local topography change the soil beneath you? Next time you look out over a gentle valley or a steep forested hill, realize that beneath the surface, active climatic energy and passive geological constraints are continually solving the exact same equations we explored today, right beneath your feet. Thanks for joining me for this explainer. Keep learning and keep looking deeper.